Okay, let's take a look at some practice problems. And of course, I posted these to Canvas. And just before we went on break, I was discussing with my students that if you take a look at this compound in number 1 and you try to find the parent chain has 7 carbons in it, but you see that I have it numbered here with these red numbers. However, you probably noticed that there's another 7 carbon chain in here. 1, 2, 3, 4, 5, 6, 7. So 2 different carbon chains. Now, if I was to use the chain that I have highlighted in yellow, you'd have 2 substituents. You'd have an isopropyl and an ethyl. Whereas if we use the numbering that I have in red, then you have 3 substituents. So you end up with a methyl group, an ethyl group, and another ethyl group. And so which chain is the correct one? And one of the rules that's not covered in our slides, but I'll go over it with you now, is that we always seek to find the longest chain with the most branches. So we want to maximize the branching. Okay, so we know that this molecule is some kind of heptane because our parent has 7 carbons in it. And we know that we have a 3-ethyl, we have a 2-methyl, and then we have a 5-ethyl. Well, the ethyls are going to come before the methyls because E comes before M in the alphabet. So this is going to be a 3,5-diethyl because there's 2 ethyls. So we'll put here 3,5-diethyl. And then we have our 2-methyl, 2-methylheptane. And there we go. There's the name of the compound. The next one, again, we seek to find the longest carbon chain. I think it's a little more obvious in this one that the longest carbon chain has 1, 2, 3, 4, 5, 6, 7, 8 carbons in it. And we have 1, 2, 3 branches coming off of there. Now, if you look at the way that I have it numbered, you see that our first substituent is at the 3rd carbon. It's this substituent right here. It's a 3-methyl. If you had started numbering in the other direction, starting here, 1, 2, 3, then you also have a 3-methyl. And so we have to look for the first point of difference. If we use the numbering in red, our second substituent is an ethyl at carbon number 4. However, if we were to use the blue numbering system, the ethyl group would be at carbon 5, and 5 is higher than 4, and therefore the numbers that I have in red are the correct way of numbering the parent. Again, we seek to give the substituents the lowest possible numbers. If we have a tie, like these 2 methyls, then we go for the tiebreaker, which would be the ethyl in this case. So we have a 3,6-dimethyl, and we have a 4-ethyl, and the parent is octane. So we put the substituents in alphabetical order. We have a 4-ethyl. Then we have our 3,6-dimethyl, and then our parent, which is octane. Remember that whenever you have a number and a letter, they're always separated by a hyphen. And whenever you have 2 numbers, they're always separated by a comma. Also, you need to remember the prefixes. If you have 2 of the same group, you use the prefix di. If you have 3, it's tri. 4, it's tetra, so on and so forth. The next compound is a little more interesting because it's a bicyclic compound. Bicyclic compound that has 2 bridges with 3 carbons and 1 bridge with no carbons in it. We have a bridgehead here. This is a bridgehead carbon, and we have a bridgehead carbon here. Well, since both of the chains, or both of the bridges here, have 3 carbons, this bridge has 3 carbons, and this bridge has 3 carbons. We're going to number this starting at either the green or the yellow, and we want to number it in such a way that we give the first substituent the lowest possible number. Could anybody tell me, should I start numbering 1 from the yellow carbon or from the green carbon? Excuse me. Would my number 1 be on the green or the yellow carbon? It should, exactly, thank you. It should be on the yellow carbon. Why would that be? Because if I start numbering at the yellow carbon, I have 1, 2, and then I have a substituent at carbon number 2. If I had started on the green carbon, I'd have 1, 2, 3, and my first substituent would be at the 3rd carbon. 2 is lower than 3, and so I'm going to have 1, 2, 3, 4, 5, 6, 7, 8, like that. So you can see that we have methyl groups at carbons 2 and 7. So we have some kind of 2,7 dimethyl. But let's go back to our bicyclo compound. Our bicyclo compound is a bicyclooctane because it has 8 carbons. So let's write down that we have a 2,7 dimethyl bicyclo, open bracket, close bracket, octane. And inside the brackets, we list the numbers that tell us the number of carbons in each bridge. In our first bridge, we have 3 carbons, so we put a 3. In our second bridge, we have 3 carbons, so we'll put a 3. And in the last bridge, there's no carbons. There's no carbons in this bridge, and so we put a 0. So the compound is 2,7-bicyclo-3,3,0 octane. Again, stop me at any point if you have any questions. Question number 4, very similar to the first two. We find our longest carbon chain, and we find the longest carbon chain that possesses the most branching. Well, with this one, our longest carbon chain starts here, 1, 2, 3, 4, 5, 6, 7, 8, 9. And so you can see that we have a methyl group here. We have, let me just label them like this. So here we have a methyl. So we have a 3-methyl. Here we have a 4-ethyl. And then here we have an alkyl group that has 4 carbons. So this is a 5. It's either a butyl, an isobutyl, a sec-butyl, or a tert-butyl. I know you've all been studying the different alkyl groups. Could anybody tell me or identify this alkyl group? Is this a sec-butyl, isobutyl, tert-butyl, or just a regular old butyl? What would this one be? Yes, it's a sec-butyl, exactly. So this is a 5-sec-butyl. And remember that sec-butyl is hyphenated. So we're going to alphabetize according to the letter B, E, and M in the 3 substituents. So that means the sec-butyl will come first. And this compound is some kind of nonane. And so we put it all together. We get 5-sec-butyl. Next is going to be the ethyl group. We have our 4-ethyl. Lastly will be the methyl group, a 3-methyl, and we put no space between methyl and nonane. 5-sec-butyl, 4-ethyl, 3-methyl nonane. Here we go. Let's try a compound that has a complex substituent on it. I'm not going to ask you a lot of questions about complex substituents. However, you should know how to name a complex substituent. I'll just review it with you one more time. You can see that the longest carbon chain here is in the 8-membered ring, and thus this is some kind of cyclooctane. We even saw a cyclooctane this morning. And then if we have a complex substituent here, I mean, this has a total of 6 carbons in it, so we don't know any common name for it. What we do is we start by numbering off of the ring, and we number the longest chain, so 1, 2, 3, 4. So this is 1, 2, 3, 4. So this is some kind of butyl. And we have a 1,1-dimethyl. So the name of this substituent would be a 1,1-dimethyl butyl. So a 1,1-dimethyl butyl. And we put that in brackets. So we have our 1,1-dimethyl butyl cyclooctane. Excuse me. And that is how we name a complex substituent. Again, that might be worth the value of 1 multiple choice question on your next quiz. Next is drawing the structure from a name. Students usually find this a little bit simpler, and I do too. It says, what is the structure of 3-ethyl 2,4,6 trimethyl The first thing we'll do is we'll draw the parent, the octane. Octane has 8 carbons. So look, when my pencil touches the paper, that little dot that I just made, that's your first carbon. So I have 1, 2, 3, 4, 5, 6, 7, 8. On carbons 2, 4, and 6, so 2, 4, and 6, I put methyl groups. And on the third carbon, I'm going to put an ethyl. I don't have a lot of space here, so I'll kind of write it like that. But there you go. There's 3-ethyl 2,4,6 trimethyl octane. The next one is what? 3-ethyl 2-methylpentane. So same thing. We're going to start with the parent, which is pentane. 5 carbons. 1, 2, 3, 4, 5. On the second carbon, I'm going to put a methyl group. And on the third carbon, I'll put an ethyl group. And there we have it. 3-ethyl 2-methylpentane. Question number 8, what is the structure of 1-cyclopropyl 3-methyl cyclopentane? Our parent is cyclopentane. So let's draw a cyclopentane ring, which is nothing more than a pentagon. There's our parent. You could start numbering any carbon you want. I'll just start numbering here. We'll call this 1, 2, and 3. So at the first carbon, we're going to put a cyclopropyl, and at the third carbon, we're going to put a methyl. So at carbon number 1, we'll put a cyclopropyl group, which is this, and at the third carbon, we'll put a methyl. Done. So that's drawing some compounds, bond-line structures, given their names. Let's try a Newman projection. It says, draw the Newman projection for the following compound as viewed down the indicated bond. Thus, we're taking our eyeball and we're looking down this carbon-carbon bond. So let's start with our carbon that's in the front. And you can see that what's going straight down is the chlorine. So we have the chlorine going straight down. That means we have a bond coming up in this direction and that direction. We have a methyl group, that's what this denotes, and then we also have a hydrogen going in the back. Out of these two positions, which one would be the methyl group? Would the methyl group be on the left-hand side or the right-hand side, the way the viewer is looking at the molecule? Imagine that you're the viewer, right? This is your body, here is your nose, right? Here you are. This is your right hand, and on this side, you have your left hand. Yes, exactly. It's on the left-hand side. Exactly. So I'll delete all that. Oops. I'm going to delete both of those. So my methyl group is over here. The CH3 group is here. I don't like to write it that way. I like to write it like this, where the carbon is closer to the bond. That. So I write it kind of in a backwards fashion because, again, the carbon is what's attached to this carbon here, not a hydrogen. And then I have the hydrogen out here. For this carbon, the carbon in the back, remember we use a circle for that one. We'll put a circle like this, and then it's going to have a bond going straight up, and then 2 other bonds that are 120 degrees separated from it. So what's going straight up is another methyl group. Here, we'll put the methyl group. And then I have a bromine going in the back of the page with the screen, and I have a proton coming out. So would the bromine be on the right-hand side or the left-hand side? Could anybody tell me, would the bromine be on the left or the right? Could anybody tell me where the bromine would be? So if the bromine is going into the page, it's going to be on the same side as the hydrogen that was going into the page. It's going to be on the right-hand side. So we have our bromine over here, and we have our hydrogen over here. Somebody asked me, how do you know whether to draw the Newman projection right side up or upside down? Well, I think of if this is the top of the page, right? The page is oriented in this direction. The way that I drew the eyeball, I have the eyelashes up here. So this is the top of the viewer. This is the person's head, and their feet are somewhere down here, right? So that means that this bond is pointing down and this bond is pointing up. Does that clear it up a little bit? Okay, cool. All right, let's try another Newman projection. So here we want to draw the Newman projection. Again, we're going to put our eyeball and we'll put our eyelashes up here. So when the viewer is looking at the molecule, what's going straight down? Right? If it's not on a dash or a wedge, that means it's in the plane of the board. That means it's going straight down from the viewer. So we have a methyl group going down here. Then we have another bond like this and another bond like this. We have a chlorine on a wedge, and then we have a hydrogen on a dash that isn't shown. Well, if the chlorine is coming out, that means it's on the left-hand side of the viewer. So the chlorine would be here, and our hydrogen would be up here. For the carbon in the back, we draw our circle. We have a bond going straight up, and these two bonds. So what's going straight up? What's in the plane of the board or the screen? It's the chlorine. Chlorine is going straight up. Then I have the bromine on a wedge. Well, if you're the viewer and you're looking at the molecule, if the bromine is on a wedge, it's on your left-hand side. And so we have the bromine over here, and then we have the other methyl group over here like this. And there you go. So you got to practice manipulating these objects in your mind. It's not easy. It's definitely not easy, but it's definitely something that can be learned. Let's try another Newman projection. We'll do two more Newman projections. So number 11 says, draw a Newman projection looking down this carbon-carbon bond. So again, you're the viewer. Draw the eyeball like this. We'll put the eyelashes up here. So what do we see? What's going straight up is this ethyl group. So going straight up, you have the ethyl group. You can draw it as a bond line structure like this. You could write ET for ethyl. I don't care. It doesn't matter. I'll draw it as a bond line structure since that's how it's done here. Then we're going to have a bond going down like this and a bond going down like this. Keep in mind that we've got a proton going in the back, and then we have this methyl group here. If the proton is going in the back, that means it's going to be on the viewer's right-hand side, like this. And that means that the methyl group would be over here. I'm going to leave it as a bond line structure just so we get some more practice with those. So I'll erase that. Now, the carbon in the back, you see that you have another ethyl group. It's going straight down. So that's in the plane. So we have the ethyl group going like this. Then we have a methyl group on a dash, and we must have a hydrogen on a wedge. So we draw these two bonds like this. Okay. And so where would the hydrogen be? Well, if the viewer is looking in this direction, the hydrogen would be on the viewer's left-hand side. So we put the hydrogen over here, and the other methyl group is going to be right there. And there's our Newman projection. No. So somebody said, will the wedges always be on the left-hand side and the dashes on the right? No, you cannot make that assumption because it depends on where you're viewing it from. If I had given you this same molecule and I said, okay, I want you to look down this carbon-carbon bond, I want you to view it in this direction, then it's going to be switched around, right? Then if the viewer is looking in this direction, shown here, then the wedge, or sorry, the dash is going to be on the viewer's left-hand side, not right-hand side. So we cannot make that. You have to think about it from the point of view of which you are looking at the bond. So I'll always tell you, which bond are you looking at? It says here, draw the lowest energy conformer of the following compound as a Newman projection looking down the carbon 2, carbon 3 bond. So we number the carbons, 1, 2, 3, 4. This compound is 2-methyl-butane. And so we're going to be looking down this specific bond, right? We're looking down going from carbon 2 to carbon 3. We're looking down here, and it says draw the lowest energy. So that means we're going to draw the lowest energy staggered conformation because staggered is lower energy than eclipsed. All right, so now that we know which bond we're looking down, it's this bond to this bond. Well, in our carbon in the front, we're going to have 2 methyl groups, right? We've also got a hydrogen on here, and it doesn't matter, where you put them. We could put a methyl group up here. We could put the other methyl group down here. Doesn't matter. And then you have a hydrogen. So now we've covered these 2 methyl groups. All right. If I label this methyl group in red, and we know that there's a hydrogen here and another hydrogen here, I'm just going to erase those because I didn't put them or didn't put the hydrogen on the other one. Okay. Well, where's the methyl group going to be if we want it to be as far away from these guys as possible and we want it to be staggered? Well, you've got 3 positions. It's not going to be in this position because then it's gauche to both of the methyl groups, but it could be here or here because then it's only going to be gauche to one methyl group. I'm going to put it down here just because that's where I choose to put it. And then I'll put the 2 hydrogens here. And there's the lowest energy conformation that we could have of this compound, which is a staggered Newman projection where we have only one gauche interaction. Again, if I put this methyl group here, I would have 2 gauche interactions, but I'm minimizing them. Number 13 is nothing more than practicing, putting in all the axial hydrogens in equal. It just says put in all the axials. So we should have 3 pointing up and 3 pointing down, right? For the axial positions that are going up, we should have 1 going up here. Then we skip a carbon, 1 going up here, and then 1 going up here. We alternate up an axial, and then next is going to be down an axial. Then blue is up an axial, then down an axial, then blue is up an axial, and then red is going to be down an axial. I like to kind of break the bond here to show that this bond is behind this shaded bond here. But there you go. Those are all the axial positions. You should also be able to draw in all the equatorial positions. We could get some practice on that too. And remember that they alternate as well. If you have something going up and equatorial, then you skip, and the next bond is going to be up and equatorial. Then you skip, and the next bond is going to be up and equatorial. So they alternate up and equatorial, down and equatorial, up and equatorial, down and equatorial, up and equatorial, down and equatorial. And so we've put in all the axial and equatorial protons on these 2 chairs. Let's get some more practice drawing some conformers of chairs. Here we have an alcohol. This compound is called cyclohexanol. You don't have to know how to name an alcohol. That's something that's covered in organic chemistry too. But we have only one substituent on the ring. The substituent could be either in an axial position or an equatorial position. So let's draw a ring. We'll start with this ring over here, and then we'll flip that. And we'll flip that ring, and then we'll draw this conformation as well. Okay, so let's just imagine that the hydroxyl is going up. Doesn't matter if it's down or up, doesn't matter. So we have up and axial here. So when I flip the ring, it's going to be up, but now it's going to be equatorial, right? What I've done is when I flip the ring, this carbon moves down here. And if you're wondering, well, why couldn't you have drawn it down? If you had drawn it pointing down, you'd get the exact same answer. Let me prove it to you, because it's mono-substituted. It doesn't matter, right? If I had drawn it going down and axial, when I flip the ring, and I'm just kind of drawing these very quickly, when I flip the ring, it's going from down and axial to down and equatorial. So you still get the same answer, right? You get one where it's axial and one where it's equatorial. So I'm just going to erase this for now so it's not too confusing. Out of those 2, if I call this one A and I call this one B, who could tell me which one is going to predominate at equilibrium? Would it be A or B that will predominate at equilibrium? One of these is going to predominate. Yeah, it's going to be B, right? Because in A, axial interactions, which are not present. And so B will predominate. So we'll put a bigger arrow to show that at equilibrium, it's mostly B with only a little bit of A. Okay, it says draw the most stable chair conformer of the most stable isomer of 1-ethyl 3-isopropyl cyclohexane. So we've got a cyclohexane like this, and on carbon number 1, we've got an ethyl group, and on carbon 3, we've got an isopropyl. So we want to draw the most stable conformation possible. Well, the most stable conformation is going to be one where everything is equatorial, right? We want to have everything equatorial, because we know that equatorial substituents are more stable, or lower in energy, I should say, than an axial substituent. And so if we just draw a chair, this, Okay, I told you kind of a convention that our book likes to do is something like this, where this carbon is the one that's going up and to the right. So let's draw the ethyl group in the equatorial position. So we'll have our ethyl group like this, equatorial. Then we skip the yellow carbon. Then we come to the blue carbon. And at the blue carbon, we have our isopropyl group, and let's draw it equatorial. So remember that the equatorial bond should be parallel to these two lines. So we draw our bond going off in the same direction as those two lines. So there's our CH, CH3, CH3. So both substituents equatorial. All right, let's move on to question 16, which asks us which one of these isomers is more stable. Now there's a couple of ways you could do this. You could analyze it from the point of view of could either of them have both substituents equatorial, or you could try to draw the chair of both of them. I mean, both ways will work. But let's see if we can solve this just by looking at the wedges and dashes. Let's imagine that this group is equatorial. So we see that it's up. If this is up in equatorial, that would mean that if I have a substituent here going down, that this would be down in equatorial, because equatorial and axial alternate. So that would mean that this one, if it's down, it's not equatorial, because down alternates equatorial and axial. So that means that this substituent is equatorial and this substituent is axial. And if you're saying, well, just flip the ring, Mr. Dion. Well, if I flip the ring, that would mean that this substituent would become equatorial and this one would become axial. So it doesn't matter. When I flip the ring for number one, I'm always going to end up with something that's axial. So let's try the same exercise. If this group is up, and let's imagine it's equatorial, because we know equatorial is more stable than axial, that would mean that the hydrogen here that's pointing up would be up and axial. That would mean that this methyl group is pointing up and equatorial. And so we can have a conformation where both of the substituents here are equatorial. And so the most stable of these two stereoisomers is going to be number 2, because you can have two substituents that are in the equatorial position. Give me a thumbs up if you follow me on that one. Why are you guys not seeing this? Can you see my screen? Can you see what I'm looking at? Okay, because it's frozen on my screen. All right, so if I move down to question 17, can you all see question 17 now? Yeah, okay, I'm gonna just stop presenting here for a second and go back in. Stop. And go back here. So let me just stop presenting for a second. So let's try this share screen. Okay, that's better. Now I can see. All right, so that was the answer to 16. And again, you could draw the chairs there, but it's not necessary. In 17, are these two substituents cis or trans? Could anybody answer that? Are these two substituents on the same face of the molecule or opposite face of the molecule? You have two methyl groups. It's some kind of 1,3. Yeah, they're cis, aren't they? Yeah, absolutely. Because this methyl group is pointing down. This one is down and equatorial. And this one here is down and equatorial. Right? This would be the axial position going straight up. This would be the axial position going straight up. And so since both of those groups are pointing down, that means they're on the same face of the molecule. And so the name of this molecule would be cis 1,3 dimethyl cyclohexane. All right, next one. This one is tricky. It says draw a wedge and dash structure of the following compound. So here's what I'm going to do. This carbon that I'm highlighting in blue, this little guy here, I mean, you could just give it a dot or something like that. I'm going to make that the carbon on the left. And then the red circle, okay, this one here, I'm going to make that the carbon on the right. So that will be this carbon here. And then I'm going to connect those two carbons with a bond. And then we're going to draw what's on the blue carbon. So what's on the blue carbon, going straight up, I have this methyl group. So that carbon's going to be in the plane. Or that bond is going to be in the plane. Then I have a dash and a wedge. Again, you're looking at it from here. It's like you're standing here and you're viewing the molecule from here. So if you're twisting the red part over to the right-hand side, what's going to be going into the page would be this methyl group. And so I'm going to have that methyl group going into the screen like this, and then I'm going to have the hydrogen coming out like this. On the other carbon, again, since you're twisting the red carbon off to the right, what are you going to see going straight down? Is going to be the ethyl group. And so I'm going to draw a line to the ethyl group, which is in the plane. Then I'm going to have a wedge and a dash. So what's going to be coming out towards me? Well, since I'm twisting it to the right, it's the methyl group that's going to be coming out, and this hydrogen that's going to be going in back, like that. This is one of those examples where it's really, really handy to make a model. So I'm going to make the model here. Just bear with me here for uno secunda. So let me just grab a couple of items here. My daughter is in Spanish school right now, so I really want to learn Spanish. And my office mate, Dr. Diaz, would tell you that I'm about the worst. But hey, doesn't mean I can't try. Let's see here. So I've got the methyl group like this. It's kind of hard for me to show you the model of this because it's going to look slightly different. But I'll show you the premise. You know, the main idea is here. So here's the molecule. Go to application. I kind of have to turn it around for you, like this. But anyhow, the bottom line is that you have, here's the carbon-carbon bond. You've got a methyl group. Where am I here? A methyl group in the plane. Get something going in back. And then you have a methyl group coming towards you. And then you have the ethyl group in the plane. So what you do is you're going to turn the molecule and look at it like this. Is kind of what you're doing. And this is the opposite of what you see because I'm looking at it like this. So for you guys, it would be looking at it like this, kind of. Anyhow, but you can see how a model can be really handy to help you master that. Anyhow, let's move on. What's the next question about? Combustion. So just a straightforward combustion problem. And this is something that you would have learned in General Chemistry 1, how to balance a redox reaction. So this compound here, 2-methylbutane, the formula is C5H12. So the rule is whenever you're balancing a combustion problem, save O2 for last. That's all you got to do is do the oxygen last and you're good to go. So let's just move this over here. So that's the rule. We have 5 carbons in the starting material. We have 5 carbons in here. So we have 1 carbon in CO2. So we put a 5 in front of here. We have 12 hydrogens in the starting material. We have 2 hydrogens in water. 2 times what gives you 12? It's 6. Then we tally up the total number of oxygens on this side. Could anybody tell me how many total oxygens do I have in the products combined? The total number of oxygens in the products. 16, exactly. So if I have 16 oxygens, if I have O2, what times 2 gives me 16? The answer is 8. You're done. So there you go. The entire thing is balanced. Question number 20. What's the relationship between these two compounds? the formula for this compound is C5H12. This is pentane. And the formula for the other compound is C5H10. This is cyclopentane. So these are not constitutional isomers. They're completely different, and they're not constitutional isomers, right? They're not identical, that's for sure. And they're not constitutional isomers because they have different molecular formulas. Let me just show you one more thing about alkanes and cycloalkanes. I showed you this in the first day of this chapter. Whenever you have an alkane, the formula is always CnH2n plus 2. But when you have a cycloalkane, if you haven't noticed this already, the formula for a cycloalkane is always CnH2n. H2n. Right here we have 2n plus 2, right? C5, so 5. And then we take 2 times 5 is 10, plus 2 gives you 12. Here we have 2n, C5, so H2n is 2 times 5, H10. There we go. So this is another rule you can hang your hat on. I would memorize this rule. Memorize this rule. Second to last question just says draw the ring flip of these compounds. So we're going to use the same old rule, where if this carbon in blue is up and to the right, then it's going to be pointing down and to the right. So up and to the right, down and to the right, up and to the right, down and to the right. So in the first one, we go 1, 2, 3. We're going clockwise. So we have 1, 2, 3 going clockwise. If this tert-butyl group is up and axial, that means it's still going to be up, but now it's going to be up and equatorial. If the methyl group here on this carbon is going up and axial, that means it's going to be going up and equatorial. And so it will be going up in this direction, so up and equatorial. In the next one, we have the chlorine going down and equatorial. So if the chlorine is going down and equatorial, that means in here it's going to be going down and axial. Then we skip this carbon in yellow. Then we go to the next carbon. I'll highlight it in red. So if the methyl group is going up and axial, it means in here it's going to be going up and equatorial. Then you have the chlorine that's going up and equatorial. So that means in the next one it's going to be going up and axial, like this. In the next one, we have the fluorine going up and axial, which means it's going to be going up and equatorial in here. Then we go to the next carbon, and the hydroxyl is up and equatorial. That means that the OH is going to be up and axial here. And then the methyl group is down and axial. So that means it will be down and equatorial in this. And there you have it, my friends. Up and axial are going to alternate as we flip the ring. And the last one is just naming a bicyclo compound. So we've got the bridgehead carbons. This is a bridgehead, and this is a bridgehead. We have 2 bridges with 2 carbons, and then we have 1 bridge that has 4 carbons in it. So we want a number going to the longest bridge first. And are we going to start with number 1 on the green carbon or the yellow carbon? Remember, I want to give the first substituent the lowest possible number. So should I start on the green carbon or the yellow carbon? Remember, I have to go to the green ring first, because I always want to start with the longest bridge. So that means I would have to start at the green carbon, right? Because if I start at the green carbon, then I give the first substituent the number 2. If I had started at the yellow carbon, I'd have 1, 2, 3, 4, 5. I'd give the first substituent the number 5, which isn't the lowest possible number. So I've numbered my first one. So I have 1. Let me just delete that. There we go. So I have 1, 2, 3, 4, 5, 6. Then I'm going to go to the blue bridge because I want to give these dimethyls the lowest possible number, 7, 8, and then 9, and then 10. So I've got a 2,7,7 trimethyl, 2,7,7 trimethyl. I've got bicyclo, and it's a bicyclodecane. So I'll put here bicyclodecane. In the longest bridge, I've got 1, 2, 3, 4 carbons, so 4. In the next bridge, the one in blue, I have 2 carbons. And in the last bridge, I also have 2 carbons. And so the compound would be 2,7,7 trimethyl bicyclo 4,2,2 decane. And there we have it. We covered all of the practice problems.